We started this chapter interested in entropy and how entropy changes, and ideally we didn't want entropy to change through our various pieces of equipment, for example through the nozzles, diffusers, and pumps and turbines and so forth. We wanted the entropy to remain constant, but then we went off and we figured out how to calculate changes in entropy. Well, I thought we wanted isentropic processes. So we've got a couple of equations for dealing with entropy changes of ideal gases, for example, and we'll start with one of the equations where we can calculate the entropy change S2 minus S1 for an ideal gas that undergoes some process and moves from state 1 to state 2. Now we're using the approximate analysis where we've assumed that the heat capacity is constant, but this is the equation that we had last time. Now, if we have an isentropic process, that means the entropy at the beginning and end of the process are exactly the same. So delta S, S2 minus S1, is equal to 0. If that's the case, then we can rearrange the terms in the equation, setting one term equal to the negative of the other. And if we want to get rid of that negative sign, the multiplication in front of the natural logarithm is just like raising the argument of the natural logarithm to the power. So basically we have a -1 multiplier, which we can put on the exponent or as an exponent of the ratio that is in the argument for the natural log. And all it does is just obviously flip the specific volume. So where we had V2 over V1 before, now we have V1 over V2. We're just using rules of logarithms to get rid of that negative sign. And then if we put all of the constants in the equation together, the gas constant and now the heat capacity as a multiplier in front of that natural logarithm, well then we can again use the rule we used with the negative sign and raise the argument of the natural logarithm to that multiplier in front of the natural logarithm. So that's all we've done here. Now the heat capacity Cp is equal to the heat capacity Cv plus the gas constant R. Plus, we've already mentioned that we define the ratio of heat capacities as Cp over Cv. Cp is always bigger. It's the heat capacity at constant pressure. So that's the definition here of K. And with a little bit of algebra, you can show that R over Cv, which is the exponent we've been playing with, is simply K minus 1. It's the ratio of the heat capacities minus 1. Now, if the natural logarithm of something equals the natural logarithm of something else, those two somethings must be equal to each other. So you can also look at this and say, well, the equation we had, we're going to raise e to the power of both sides. Or you can just say, well, if the natural logarithm of the argument on the left equals the natural logarithm of the argument on the right, those two arguments have to be the same thing. They have to be equal to each other. And that's what we end up with here in the equation in the box. It relates the two temperatures at the two states to the specific volumes at the two states. And you might wonder why we need this, because after all, isn't this an ideal gas and don't we have the ideal gas law? Well, we have, but think about the ideal gas law. It has pressure, volume, and temperature in it. Oh, but wait a second, it has pressure, doesn't it? It has 3 different variables, whereas this equation only has 2. Now, this equation is not something you can apply to every ideal gas. This only works when the ideal gas undergoes an isentropic process. If you know that the entropy is the same in state 1 and state 2 of the ideal gas, then this equation applies. Now, all the derivation, the math is nice, but if you don't remember or understand all that, it's okay. This is what we call the first isentropic relation, and it's good for almost all of the devices you see here. Now notice that we made a big assumption in our derivation of this equation. There are several things that are built into it. Okay? We assumed isentropic behavior. That's the first thing, is that this is an isentropic equation. It assumes that the initial and final entropy are equal. So if you think of a nozzle, the entering entropy and the exiting entropy of the fluid should be the same if it's an isentropic nozzle. Same with a diffuser, this turbine, or even the compressor. The only thing is, if we have a process where there is heat transfer, then certainly the process is not isentropic. So for a general compressor that doesn't have any heat transfer, this equation would work fine. But for the example that I've drawn here, where there is some heat transfer, this equation would not apply, because this is an isentropic relation. In other words, it only works for processes where the fluid undergoes some type of isentropic process. And obviously if there's heat transfer, the entropy could decrease by the time we get to the outlet of that compressor. So this would not work. But it does apply to the other pieces of equipment, and it would apply to an air compressor that has no heat transfer just fine. So it's really important that you know what the restrictions are on this equation. Number one, it has to be an ideal gas. This doesn't work for liquids, and it doesn't work for real gases either. We have to be able to assume that the heat capacity is constant. Now, how does that appear? We don't really see that obviously in this equation. Well, remember that K is the ratio of heat capacities, and the K is a number you're going to look up. It's going to be one number and it won't vary. Therefore, we are assuming constant heat capacities. Also, this equation only works for isentropic processes. In other words, processes that are adiabatic with no heat transfer and that are also reversible. Now, I realize there's no such thing as a purely isentropic process, but ideally our equipment would operate isentropically and give us, have the lowest friction, have the lowest irreversibilities in general, and require the least amount of work to perform what they're supposed to do or generate the most amount of work out, if that's like the steam turbine is supposed to generate work out. So it's really important to know what the restrictions are on this equation. Now, it's also important to know where it is, because if you're like me, you're going to forget exactly what order the subscripts go in, and is it K minus 1 or is it K, because we're going to see some more equations like this and it can get confusing pretty quickly. At this point, go to the back of the chapter and find this equation. Make sure that you highlight all the notes around that equation that tell you what the restrictions are, because they are there. It's just in this author's book, sometimes what he'll do is put a whole bunch of equations together that have one restriction, and he'll put that restriction at the beginning, like for ideal gases, all these equations apply. So be careful and make sure that you find this equation number one, and that you make it obvious to yourself that these restrictions are restrictions on that equation. It has to work for an ideal gas, constant heat capacity, and an isentropic process only. Now remember, there were two different equations we could have begun with. We had two tedious equations, remember those? And one involved a temperature and volume ratio, the other one involved a temperature and pressure ratio. That's the one we see here. One seemed to relate closer to enthalpy because it had a constant pressure heat capacity. The one we just played with was related to internal energy because it had a constant volume heat capacity. But we could use this equation just as well as we did the last and say, well, here's an equation that allows us to calculate entropy changes for an ideal gas. What if the entropy change is 0? Well, then we don't have a negative sign to contend with, and rather than using the negative sign as an exponent on the pressures and flipping the subscripts, we don't need to do that. We can go directly to the step of putting the constants together, the gas constant and the constant pressure heat capacity, and then raising the argument to that constant ratio as a power. Okay, so now again we've got the natural logarithm of the temperature ratio equals natural logarithm of the pressure ratio, where the pressure ratio is raised to the exponent R over Cp. We'll use the same equations we did last time, where we realized the constant pressure heat capacity is Cv plus R, and the ratio of heat capacities is Cp over Cv. With a little bit of algebra, you can show that the ratio of R, the gas constant, over Cp, which is our exponent, the constant pressure heat capacity, is equal to K minus 1 over K, where K is the ratio of heat capacities. Again, the arguments must be the same because the natural logarithms of the arguments come out equal, so we can simply write that the temperature ratio equals the pressure ratio to the power of K minus 1 over K. So that was a lot of math. Again, does the math really matter? Well, not necessarily. It's consistent, it's correct, and it's in the back of the chapter in your book. And it's the second isentropic relation. That's what I'm going to refer to it as because it appears second in your text. It has the exact same restrictions as the last equation because it's an isentropic relation. There can't be any heat transfer, so again, it doesn't work for this particular compressor. It would work just fine for a compressor that had no heat transfer and that was reversible. In other words, that was isentropic. The same restrictions apply to this equation because we've made the same assumptions. It has to be an ideal gas that this equation works on. We have to be able to assume constant heat capacity during the process. In other words, the temperature change of whatever fluid is flowing through these things needs to be fairly small. It can't be some 1,000 Kelvin change in temperature. It has to be an isentropic process. In other words, there has to be no heat transfer and it has to be reversible. Now you may have noticed that the first and second isentropic relationship look quite a bit alike. They both have a temperature ratio on the left-hand side. We can derive another equation, but it is not independent of the first two. In fact, we put the first two together to get it. You'll notice the left-hand sides of both are the same. They're just temperature ratios. So the right-hand sides must be equal as well. Turns out we can actually simplify the exponents a bit, and here's what you end up with. It's a little bit easier math than what we've played with so far, but there's the result. It's a pressure ratio related to a volume ratio, or a specific volume ratio. This is the so-called third isentropic relation, and you'll notice that it appears in the text just below the other two in the summary, and I highly recommend that you highlight them or something because we're going to use these quite a lot. It has the same restrictions, doesn't work for any non-isentropic process, such as ones that have heat transfer. This only works for ideal gases with constant heat capacities and so forth. So these are the three isentropic relations, and we call them approximate analysis because they don't take into account the variations of heat capacity, so they don't apply over as wide a temperature range as sometimes you would like. Now we can do an exact analysis, or something much closer, where we're still keeping the assumption of ideal gases, but we're going to so-called relax the assumption of constant heat capacity. That doesn't mean we get to relax. That means it's actually a little more difficult. Let's go back to our tedious equations. We had one that involved enthalpy, and here it is. It was a differential equation, and we can make the substitution of dH equals Cp dt and insert the ideal gas law for the specific volume. This is what we did before, and we ended up at this point where we realized we could integrate the last term easily, but we needed to integrate the heat capacity as a function of temperature. And that's the point where we took our left turn, if you will, and we said, well, let's just assume that the heat capacity is constant. That way we can take it out of the integral, and that's why that first natural logarithm term came from. But what if we don't do that? Well, we don't have to necessarily. What we could do is actually perform the integration. Now, I know we're engineers and we're lazy. I mean, we're efficient, right? We'd like to not do that. So a lot of times the way engineers and scientists solve problems is they solve all the problems they can now so that later on it's easier to solve particular problems. And what do I mean by that? Well, if you think about this integration, we're going to integrate over some range of temperatures, right? From temperature 1 to temperature 2. Well, couldn't we integrate from absolute zero temperature all the way up to 1 temperature? And wouldn't that represent the area under the curve for this function, the Cp of t over t? And then couldn't we take the difference? In other words, if we wanted to, we could define a parameter and call it S naught and integrate from a temperature of 0 to every temperature we might be interested in, right? It'd be a lot of work, but we could do it to 1 Kelvin, to 2 Kelvin, to 3, to 4, to 5. And while we probably wouldn't really want to integrate to all of those, we could probably write a computer program that does this fairly easily, because in fact we do have the heat capacities as a function of temperature in the back of our text as polynomials. So we could do this, but actually it's already been done for us. And I don't remember the exact resolution. I think it's every either 5 or 10 Kelvin or so, something like that in the metric. In the English appendices, I don't remember. You'll have to go back and look at it. You should go and look at that now. It's either table A17 or table A19. And I can't recall which one, but it's one that you'll want to mark in your book. You need to go and look at it because when you look at this table, it's, for example, the one I referred to you to is the ideal gas properties of air. And there are some other tables for other gases as well, and they all follow the same format. But in that table, there's several different things. They've got the internal energy, they've got the enthalpy, they've got, all as a function of temperature, but then they've got these S naught parameters, and you will be very tempted to call the S naught parameter the entropy. Okay, you'll get used to looking at tables in the back of the book and reading off entropy's S, and when you see an S naught, you'll think, well, I guess that naught really doesn't matter, it's just entropy. Actually, it is not entropy. It's the integral of Cp as a function of t over t from a temperature 0 up to whatever temperature you've got in that particular row. So you should be looking at the table at this point to understand this. So S naught is not entropy. It's this area under the curve from 0 temperature all the way up to various temperatures of interest. Now, why is that useful? Well, because what we could do is, instead of worrying about always integrating from T1 up to T2, we could simply integrate from 0 to T2 and subtract off the area under the curve from 0 to T1. So remember from calculus, when you wanted to evaluate an integral, you could break it up into parts, right? You could integrate from one temperature to, an intermediate temperature and add that to the integral from that temperature onto T2, or, like we're doing here, integrate from some point farther out, like 0, all the way to the temperature. That's going to give you a certain amount of area under the whole curve to that final temperature, and then subtract off the little bit at the beginning, which is the integral from 0 to T1. And that's all that's being done here, is the integral from 1 to 2 has been broken up into two parts. And of course the reason for doing this is we could perform this integration from a temperature of 0 to multiple different temperatures, and once we get that done, we could interpolate between the temperatures. We don't really have to integrate to every exact temperature. It's nice to have this data tabulated, and that's what the appendices that I referred you to already are about, table A17 or 19, whichever it is. So we get to substitute, for integration, we substitute these S0 parameters. So the value in the S0 parameters is for calculating the entropy change, but these S0 parameters are not the entropies themselves. Okay, there's this other term, minus R natural logarithm P2 over P1, that must be included. And so this is how we will calculate entropy changes of ideal gases if we want a more exact analysis. And in my opinion, this is actually easier than even using the heat capacity, because before, what did we have to do? Well, we took the heat capacity times the natural logarithm of the temperature ratio. Remember that? And here, all we have to do is look up the two temperatures, look up the two S0 parameters, and plug it in. The only time when that's probably a little more difficult is when we have to interpolate. But interpolation is not all that difficult, and if you think it is, you should make a function in Excel or on your calculator if you have a graphing calculator, or even you can probably get an app for your smartphone if you want to that will let you interpolate very easily. So that's a problem you should be able to manage. We're going to do a lot of interpolation in this class, and you should get used to it and make it so that it's easy for yourself. Make it easy to perform. And I don't care if you use Excel on exams or any of your smartphone apps for calculating entropy changes. That's fine. What's nice about this is it's a more precise analysis than what we had before, where we assumed that the heat capacity was constant. Now the drawback is we have to have tables of these S0 parameters. You probably don't want to go through and create them, right? You don't want to create them for various gases, even though we have the heat capacity as a function of temperature in the back of our book for various gases. I suppose you could write a spreadsheet, and the integration is not all that difficult because, quite frankly, it's just a polynomial. But it's already been done for us for air, and that's the primary gas we will use this semester. If you need it for others, you can get it, or it's actually in the book. The interesting thing is, though, for air it has the, how does it go? It's per unit mass properties, whereas I believe many of the other tables, the ideal gas properties, are in per unit mole. So you got to use the molecular weight to convert it, but again, it's easier than doing the integration yourself. So the restrictions on this equation are a little bit less than what we had before. We're still working with an ideal gas. We still have to assume where the gas has to behave ideally, or at least close enough to it where we can assume that. And are we assuming constant heat capacity? No. We've relaxed that one. That one's gone. The only assumption so far is that we're dealing with an ideal gas. That's it. Now, before, what we did was we came up with some equations that allowed us to calculate the entropy changes of ideal gases, and we said, well, wait a second, the equipment we're working with may have an ideal gas flowing through it, but what we would like to do is we would like to calculate or get equations that tell us about how these pieces of equipment should perform if they're acting isentropically. And so what we did was we said, okay, we can calculate entropy changes, but what if there is no entropy change? What if S2 and S1 are equal to each other? In other words, the inlet ideal gas properties, well, in particular, its entropy is equal to its entropy at the exit. The other properties obviously are going to change if the equipment is doing what it's supposed to do. So what if there's no change then in the entropy? Well, then we could put the S0 parameters on one side and the natural log and gas constant on the other, and then we could recognize that R and the S0s are basically just constants. Right? We can look up those constants S1 and S2 based on the temperature. So let's put the gas constant with those, and let's get rid of the natural logarithm by raising both sides to the power of E. So that means on the left-hand side we're left with a pressure ratio. On the right-hand side we've got E to the power of the difference between the S0s over R. Now, it's a little bit inconvenient to have it this way because we have to look up the S naughts and we have to hit E on our calculator. And the rules of exponents tell you that this e to the S naught 2 minus S naught 1 over r can be broken up into two parts, right? One that's in the numerator and one that's in the denominator. And so that's what's been done next. If we define the e to the S naught over r numbers as just a separate single number, we could actually calculate these, right? We've already got the S naught as a function of temperature, so all we'd have to do is raise e to that S naught over r, and that would be just one number that corresponds to a particular temperature. So rather than going through the effort of saying, okay, well, I know I've got this temperature in state 1, I've got this other temperature in state 2, that lets me get the S naughts, look up the gas constant, calculate e to the S naught over r, and then take those, for both state 1 and state 2, and then take the ratio. Instead of doing that, we can just tabulate it. I mean, we may as well. We've got this whole table anyway. So make sure you're back in the table, the ideal gas properties of air table, and you'll notice that there are PR columns for the gas. And they're tabulated there. They're just numbers. Unfortunately, this looks like something we've seen before. This particular thing is called the relative pressure. But we've already used the symbol P sub r for reduced pressure. Please don't confuse the correction of the ideal gas law with compressibility. Don't confuse what we're doing there, the PRs there and the TRs and so forth, with this PR. This PR has more to do with isentropic processes, and we'll call this the relative pressure. And then we can make our equation look very simple, right? This pressure ratio then equals a relative pressure ratio, where these two relative pressures can be looked up as a function of the temperature in the two states. Or, better yet, if we know the pressure ratio and we know a beginning state, then we can look up the PR for that state, because we have the temperature, and then use this equation to calculate the temperature in the next state. Well, the relative pressure in the next state, which we then back out to the temperature in that state. So if you understand all that, great. We're going to use it enough that hopefully it will make sense. But here is an isentropic equation. It's as valid an isentropic equation as the first, second, and third isentropic equation. As a matter of fact, this one's even better, and look at it. It looks easier to use. It doesn't even have an exponent on it. Okay, but it's basically relating pressures to temperatures. Now, don't be confused here. I know it looks like it's a pressure ratio related to a pressure ratio, but in fact the PRs are temperature dependent, right? You get those from the table. So it's really relating a pressure ratio to some function of temperature is what it's doing, but in an easy way to make our lives easy. Now, this doesn't apply to the process where we have any heat transfer, because again, this is an isentropic equation, and there are restrictions on it. Number one, it's based on an ideal gas, right? We can only use this on ideal gases. It won't work for liquids at all. Okay? And also the process has to be isentropic. Notice that there is a restriction that's missing that we had with the first, second, and third, and that is the restriction of constant heat capacity. That is not a restriction here. So this is actually a better equation than the first, second, and third, and will give us more precise results. Now, I went through the description of how to use this pretty quickly, but I like this graph from your author's book because it explains exactly what you do. If you know, say, the temperature in state 1, and you know that state 2 is isentropically related to state 1, you can get a very accurate answer very quickly by simply taking the temperature in state 1, look up the PR in state 1, the relative pressure, calculate the pressure ratio. You'll have to know the pressure at the exit and at the entrance. That'll give you P2 over P1. Multiply that by the relative pressure in state 1, and that gives you the relative pressure in state 2, which then you go and you look up the temperature in state 2. So this makes it pretty straightforward for calculating the temperature at the exit. Now, honestly, what usually happens is you end up on a line, well, between two lines, and you have to interpolate to get T2. But it's really not all that bad, especially, as I said, if you have an interpolator set up for you. Now we can do a little bit more with this. We don't have to restrict ourselves to that one isentropic equation, because if the process involves an ideal gas, which was one of the assumptions we had, then that gas is related by the ideal gas law between the first and second state. So P1V1 over T1 equals P2V2 over T2. You can get this by starting with the the ideal gas law and realizing that the mass and the gas constant are constants, and so this relation just falls out of that. From this, we can rearrange a little bit to solve for the volume ratio V2 over V1 in terms of the temperatures and pressure ratios, but we know from the isentropic equation before of P2 and P1 equals PR2 over PR1, we know we can replace the pressure ratios by things that are functions of temperature, PR1 and PR2. So you'll notice after the second equal sign, that's what's been done here. And then the state properties are put together in the last, after the last equal sign, so that T2 over PR2 over T1 over PR1 is grouped together nicely. So we've got state 2 in the numerator and state 1 in the denominator. If we then define another term called the relative volume, VR, as the temperature divided by PR, this is another thing that can be tabulated and save us a lot of time, because look, we can then say that V2 over V1 equals the relative volume in state 2 over the relative volume in state 1. So that's the last column you'll notice that we haven't discussed so far in that ideal gas table for air. This should be the one you're still looking at. Okay, so this is another isentropic relation, and which one would we want to use? Would we want to use this one or the one that involves pressures? Well, they're both equally valid. Use whichever one is more convenient for your purposes. A lot of times we'll stick to the pressure relationship, the pressure isentropic equation. But here we've got a volume-related isentropic equation. Now understand that it's volume on the left-hand side, V2 over V1, but VR2 over VR1 is a temperature-dependent thing. So don't think of the VRs or the PRs as being volumes and pressures. Think of them as being functions of temperature, because that's what they really are. It obviously will not work on this device that has some heat transfer. And the reason it doesn't work there is because this equation is another isentropic equation. It only works on ideal gases. That's built into the equation. It only works for isentropic processes as well. Now the way we use this is very much the way we use the relative pressures. You simply use your whatever temperature is known to find the relative volume, then use the isentropic equation to go from the relative volume in one state to the relative volume in the other, assuming we have the volume at the initial and final states, and then read off the temperature in the second state.